Thrust and pressure. One thread a nail into a piece of wood easily by applying force over the head of the nail. However, the reverse is not possible. When the force is applied over the tip of the nail, it will not penetrate into the wood. In both the situations, the applied force is the same, but the effect is different. The same force may create a large effect or a small effect depending on the area it is acting on. In fact, the amount of force per unit area determines the effect of the force. This quantity is called the pressure. It is the amount of force spread over a unit area. Pressure can be defined as the normal force acting per unit area. The normal force acting on a given surface area is called thrust. Hence, pressure can also be defined as the thrust per unit area of the surface. We know force is a vector quantity and area is a scalar, but pressure is also a scalar quantity. Do you know why? Here, F appearing in the numerator is the component of the force normal to the area under consideration, and thereby not a vector force. That is why pressure is a scalar quantity. The SI unit of pressure is Newton per meter square. It has been named as Pascal in honor of the French scientist Blaise Pascal, who carried out pioneering studies on fluid pressure. It is clear that the same force may create a large pressure or a small pressure depending on the area it is acting on. In fact, smaller the area on which the force acts, greater is the pressure. That is why a blunt object produces a low pressure because it has a wider contact area, whereas a sharp end has a very small area, so the same force produces a very high pressure. Pressure can be increased either by increasing the amount of the applied force or by decreasing the area. For example, when we press our finger against a balloon, not much happens. Our finger causes a small depression. On the other hand, if we push a needle against the balloon with the same force, it bursts. Because the same force applied to a very small area causes a large enough pressure that ruptures the balloon. In general, a high pressure is required while cutting, sewing, and so on. Both pins have pointed ends, so that a small force applied over the head of the pin may allow it to penetrate into the surface easily. On the other hand, a low pressure is required while moving or holding something, such as a camel can walk on sand easily because the area of camel's feet is large. Hence, the pressure is lower and his feet do not sink into the sand. On the other hand, a deer cannot walk on sand easily due to the small size of his feet, which may go into the sand. Similarly, double wheels are provided in heavy vehicles to increase the area of contact and thereby reducing the pressure. Large buildings have wide foundations. This is again to increase the area and thereby reduce the pressure. Also, taller the building, larger is the foundation area. Similarly, when dams are built to stop and store water, the base of the dam is made broader than the top because its base has to sustain more water pressure as compared to the pressure exerted by the water on the top. Let's say small aquatic birds. These birds have exceptionally long toes that are spread out over a large area, and hence the weight of the birds cause only a relatively small pressure when they walk on the soft, muddy shorelines without sinking into the water. Let's summarize numerical problems. Measure the pressure exerted by an elephant of weight 30,000 Newton if the area of each foot is 1500 square centimeter. It comes out to be 50,000 Newton per square meter or 50,000 pascals. That is 50 kilopascals. Further, if the elephant is standing on one foot, then the pressure comes out to be 200 kilopascals. Calculate the pressure exerted by body on which a force of 125 Newton is acting and area of contact is 10 square meters. Using the expression for the pressure, it comes out to be 12.5 Newton per meter square. If the pressure experienced by the body is 5200 Newton per meter square and force applied on it is 130 Newton, then measure the area of contact. Area of contact can be measured as the ratio of the applied force and the pressure that gives area equal to 0.025 meter square. A substance that can flow easily is called a fluid, such as liquids and gases. Similar to a solid, a fluid also exerts pressure and can be used for pressure transmission. In static fluid, the pressure acts equally in all directions and acts at right angles to any surface. Let's take a fluid element in the form of a horizontal bar of uniform cross-section. For the bar to be in equilibrium, the forces exerted at all the surfaces must be balanced. In the case of unequal pressure, there should be a fluid flow due to the net force acting on the fluid element. Thus, for water body in equilibrium, pressure at all the points is the same in all the directions. The same can be observed when water rushes out of the holes from a tin container having 2 or more holes at different places, but at the same height from the bottom, and the streams of the water rush out to the same distance. This also shows that the pressure on the water has been transmitted equally in all directions. This is known as Pascal's law, and it is valid only if the fluid is incompressible, that is, for liquids. This principle is most commonly used in hydraulic lift to lift heavy objects, such as vehicles at a service station. A hydraulic lift consists of two cylinders filled with incompressible oil and connected to each other with an oil-filled pipe. The two cylinders are of different areas of cross-section and are provided with frictionless pistons. When a small downward force is applied to the smaller piston, the pressure exerted over the liquid is equally transmitted to the bigger piston through the oil in the pipe, and thereby a larger force is transmitted to the larger piston. Thus, the force is multiplied by a factor that is equal to the ratio of the two areas. An important application of Pascal's law can be seen in hydraulic brakes used in vehicles. Similar to the hydraulic lift, when the driver of the vehicle exerts a smaller force on the brake paddle, it pushes a piston into the master cylinder of the brake, containing brake fluid. The brake fluid from the master cylinder is led through strong pipes to the slave pistons, one at each wheel, and each piston has a larger area of cross-section for brakes. Thus, a small force applied over the brake paddle is transmitted by the brake fluid as a large force to the slave piston for each brake. Finally, they press against the brake linings of the drums of the wheels and bring them to rest. Hydraulic jack also works on the same principle. Pressure exerted by a static fluid can be measured as the force exerted on unit surface area which is in contact with the fluid. However, liquid exerts pressure due to the distribution of its own weight. For more clarity, let's take a can and make 3 holes, but along a vertical line at different heights. Pour water into the can once again. One can observe that water rushes out of the holes. Here, we can notice that the water at the lowest hole rushes out with the highest velocity and thus covers the maximum distance. This shows that at the lowest hole, water has maximum pressure. That is, the pressure in fluid depends only upon depth or the length of the fluid. It can be seen when we insert a manometer in a beaker filled with water at a fixed depth and move the funnel back and forth, the manometer pressure comes out to be uniform. This indicates that at the same depth inside a liquid, the pressure remains the same. Further, if we insert the manometer at different levels, one can notice that greater the depth, higher is the pressure. That is, at any point in the liquid, the pressure depends on the height of the liquid column above it. Let's now take 2 beakers, one filled with water and one filled with a salt solution. If we keep the manometer funnel at same depths in the 2 beakers, it can be seen that the pressure is different in both the cases. That is, it depends on the density of the liquids, or higher the density, higher is the pressure. Hence, the pressure at a point at a depth of h in a liquid can be measured as the ratio of the weight of the liquid column and the area. Also, mass can be measured as the product of volume and density. Hence, the pressure at a point inside the liquid can be obtained by the product of its depth, density and acceleration due to gravity as shown. This shows the liquid pressure on the surface is 0, as the height of liquid column is 0. But the liquid surface is also exposed to atmospheric pressure. That is, pressure of the surrounding air on the surface. Thereby, total pressure at any point in a liquid is the sum of atmospheric pressure and the liquid pressure. Do you know the cause of air pressure? Our Earth is surrounded by an envelope of air called the Earth's atmosphere and extends up to a few kilometers. Although air is invisible, but it has weight and volume. We know that pressure is force per unit area. Hence, the weight of the air column above the point of measurement over a unit area on the Earth's surface is called air pressure or atmospheric pressure. One can measure the atmospheric pressure. It comes out to be 101 kilopascals. This is also equivalent to the pressure exerted by 76 centimeter of mercury column. This pressure is so high that it can crush many objects, including human bodies. But human bodies withstand this air pressure by creating an equivalent pressure by blood flow in the blood vessels. This fact is further substantiated by the fact that the moonwalkers on the moon put on clothes that create additional pressure to make up for the major loss of air pressure on the moon. Existence of air pressure can be seen with this activity. Take an empty tin can. Initially, pressure inside the can is equal to the pressure outside the can because it is filled with air. Take out some air from the can. For this, pour some water into the can and then boil it off. Now, the steam would carry away the air with it and the pressure inside the can becomes less than the pressure outside the can. Now, close the opening of the can and immerse it in the cold water. The steam inside the can condenses and the can gets squeezed and crumbled due to the force exerted by the atmospheric pressure on its outer surface.